Thank you. So hi, everyone. I'm Elisa Carafili from the University of Southampton. And it is my pleasure today to have as our speaker, Dr. Basel Halak. Basel is a member of the cybersecurity research group here at Southampton. He's a reader and also an Royal Academy of Engineering Industrial Fellow. Basel, are you there? And he will present us physical unclonable functions, PUFS, design principle, application, and outstanding challenges.
Thank you very much, Riza. It's a pleasure to be here. I'm sorry I had a problem with my connection, but I think it's restored now. Hello, everyone. In today's talk, I will present the principle of physically unclonable functions. In particular, I will discuss their design and evaluation matrix. I will also explain how they can be used and why we need them in the first place. And then I will conclude my talk with outstanding challenges and emerging solutions to allow for more deployability of this.
Basel, I think you need to share your screen. We don't see your screen. Perfect. We can see it.
Right. Physical unclonable functions are based on this phenomenon which is called physical disorder. Every physical object at its microscopic level display a certain degree of irregularity. And these irregularities can actually be used to uniquely identify the object. The use of physical disorder to identify physical object is not a new idea, actually. It has been used in many occasions in the past. And in this slide, you see here an example of such use, where an American defense company called Sandia used to spray a nuclear arm with special paint, and then they will shine a light on it and then record the generated optical patterns. And this will be used to uniquely identify their head and for nuclear arm inspection. Now, the same physical disorder is also present in silicon chip. This is a cross-section of the iPad mini A5 processor. And if you are to take a cross-section of different chip of the same design, then you will notice that the shapes are slightly different. And the reason for that is that with integrated circuit, it's especially with those circuits that are fabricated using technology sub 90 nanometer, it's quite hard to precisely control the manufacturing process. So we will have different level of doping, different feature size, different thickness of the oxide. And this variability of this manufacturing parameter can affect the electrical behavior of the resulting devices. In this context, we differentiate between two types of process variation. The intra-die process variation, which is basically the variability between devices, identical devices or identical design implemented on different dies, different wafers. And we also have the intra-die process variation, which is basically variability between devices, identical devices implemented on the same dies, in the same die but at different locations. Now, PUF technology exploit both type of process variation in order to actually work. So let's see how this. Now, one of the first PUF that's been developed is called Arbiter Path. So in this case, And this is a diagram of a single input, single output arbiter path. It consists of these two delay paths and an arbiter here at the output. If you feed a signal from this input, then it will travel through these two paths at slightly different speed, not speed. It will take slightly different time to reach the endpoint here, because of what we call the intra-die process variation. Because although these inverters here are supposed to be identical, but in fact, if you are to compare, for example, the threshold voltage, they will be slightly different. So this difference affect their delay, and in turn, and subsequently affect the latency of the signal traveling through them. So they will arrive at this arbiter at a slightly different time, and the response of the arbiter will be 0 or 1, depending on which signal arrives first. So we will need the intra-die process variation in order for this structure to work in the first place. Otherwise, if those two paths are identical, then we will have better stability here. Now, if you are to implement the same design on different chip, then you are going to get different output because of the inter-die process variation. And in this case, the output is just simple binary output 0 or 1. But if you are to generate an identity, a digital identity, then you simply replicate this structure. Now, Arbiter Path was one of the first paths that we designed, and in that sense, we can define path as, or silicon-based path as an integrated circuit, relatively small, which harnesses process variation and generate a unique identity for each chip. One of the problems with the arbiter design is that in order for the PUFS circuitry to work, the output should be only dependent on the underlying process variation. And because in the arbiter I have this arbiter block at the end, sometimes this arbiter block can be asymmetrical in a sense that it favors one input over the other. So the output of the path will not actually be based on the on process variation, but it will be based on the asymmetry in this arbiter design. And this asymmetry could be due to routing asymmetry, for example, which is quite hard to control in platforms such as FPGA. To overcome this problem, we have the ring oscillator path, which consists of a set of ring oscillators. Each of them will oscillate at slightly different frequency because of the intra-die process variation. We've got here a multiplexer, which is controlled by a challenge. So the challenge will, each challenge will choose two of these multiplexers to compare, and then they will let to oscillate for a period of time, and which will increment these two counters. And then at the end here, we've got effectively a digital comparator, which is basically much more precise than the arbiter in terms of comparison. So it's not affected by those asymmetric problems. So both of these designs are called delay-based path because they're based on comparing delay. We have also other type of path. We've got the SRAM path. In this case, a typical SRAM cell will consist of 6 transistors, 2 access transistors here, N3 and N4. And then we have these 4 transistors which form a cross-coupled inverters. When you power up the SRAM cell, then these 2 cross-coupled converters will fight. One of them will try to drag the other, push the other to 0 or 1. And depending on the slight variation in the threshold voltage, the output is going to be either a 1 or a 0. So this power up value of the SRAM is based on process variation and can be used also as a path. Effectively, this SRAM is one of the most widely used path, and it's already integrated in product. by companies such as Intrinsic ID. So this is already commercially available. Now, one of the problem with SRAM is that in order to generate the response of the PUF, you do need to power off and then power on the device, which can be practically difficult. So a similar structure which overcomes this particular problem is called butterfly PUF. So in this case, we have two cross-coupled D flip-flop, and then the preset or pre-signal will set them into metastability, and then they resolve to the output will resolve to a 0 or 1 depending on the variability between the underlying circuitry of these two flip-flops. Now, the problem with this design is that it's not well supported by all type of technology. Now we know what PUF is. How to judge whether a PUF, a particular design, is a good PUF or a bad PUF. For this, we've got a number of quality metrics, and two of the most important quality metrics is called uniqueness of reliability. Uniqueness is a measure of the ability of the device of the PUF design to generate a unique ID. Okay, so effectively, if you've got a PUF design and you implement the same design on different chip, it should generate different output for different chip, for assuming I'm applying the same challenge. Because that's the whole idea of the PUF. Now, the ideal uniqueness is around 50%. What does that mean? That if you are to measure the Hamming distance, so if you are to fabricate 10,000 chips, and you measure the response of the PUF of each of these chips for the same challenge, and then measure the Hamming distance between each pair of these two, and average the result, then this should be around 50%. So if you pick two PUFs randomly, the similarity between their responses for the same challenge is no more than 50%, which makes it harder to predict the output of one PUF if you manage to know the output of the other PUF. Reliability is the measure of the ability of the PUF to generate a consistent response in the presence of noise or environmental variability, which is quite important if you consider that the PUF is used in applications such as cryptographic key generation. Again, reliability, we were looking for, depending on what application you're going to use the PUF in, we have different requirements for reliability. For cryptographic key generation, we're really looking for 100%. If it's not 100%, then we need to implement some error correction code. For authentication, we might have margin for errors, so we might actually accept up to 80%, but depending on the protocol. Right. So this is an example of different comparison between the uniqueness of different designs. So you can see here, for example, here is the uniqueness for basically the RO PUF, and which is around very close to the uniqueness. And in the case of the Arbiter Path, you see it's skewed, so it's around 0.37, so 37%, which is not that good. It's skewed toward 0 or 1. So these are based on our simulations. So that's the first part. So now we know what a PUF is and how to evaluate it. What are the applications of PUF and why we need it in the first place? The first application of PUF, which is currently used and deployed in some product, is for cryptographic key generation. So the threat model, if you like, in this case, so why do we need PUF? Normally, the security depends on what we call the root key. And this root key is normally used for encryption or for other security-related mechanisms. And the root key should be inserted or stored in a non-volatile memory. And the way this is done is either done by the manufacturer of the chip or by a trusted party. Now, the problem is we can't always trust those parties to actually inject those keys. So there's too much risk in some certain applications. So therefore, we maybe need a better way to reduce, to mitigate the risk of maybe malicious trusted third party leaking those keys or actually using them to undermine the security of the device. The other problem with storing the key in the root key in a memory is that there are actually known security attacks both at the software level and at the hardware level that are able to retrieve the key from the memory. Some of these are mentioned here. So malware, you can basically access unauthorized regions of the memory, or you can use data remnants attacks, physical attacks to retrieve information from memory. So how to actually use PUF in this context? So simply, we can embed each device with a PUF. You are to generate an encryption key, then you apply a challenge to the PUF, and then you generate the key. So there's nothing stored on the device, only the original kind of product developer will actually be aware of this key because they will need to actually characterize the behavior. So before they bring the device, they will actually apply and actually record this key before start to communicate with the device using this key, for example. If there is a physical attack, they can't actually know exactly how to generate a key from this PUF because they might not be aware of the particular challenge that we have. So this is the idea. And now the problem in this case is that PUF, as any other integrated circuit, is vulnerable to noise, different form of noise. So we can't always, it's not always able to generate the exact same response for the same challenge. So in this case, what do? We can't afford to have any errors if this key is the root key. It has to be generated with 100% reliability. So the approach in this case is to use error correction code, which needs some helper data. And I'm going to explain to you roughly how to do that. Now, there are a number of techniques that can be implemented in this case. I will show you one of them called code offset construction. This is by no means the most secure, but it's probably the best in terms of illustration this concept. So we have this technique will actually consist of two stages. In the first stage, we call it the helper data generation. So the helper data generation should take place before the device is deployed in the field. And what you do, you apply a challenge to the PUF, you generate the response that you want to use as a root key, and then you XOR this response with a random code word from a particular error correction code. We'll talk about that in a minute. And then you store this resulting vector E, which is the helper data vector in helper data storage. So on the device, you will have your PUF, and you will have ideally a secure memory where you store this helper data. Once the device is deployed, if you want to use this root key, you apply a challenge to the PUF. You generate an R prime, which is basically the response to some errors. You need to XOR R prime with the helper data. This will generate E prime, which is error vector, plus C, which is code word. Now, as long as the error correction capability of the ECC code you have chosen is larger than the Hamming weight of this error vector, then you should be able to retrieve the original code word used and then export it with the helper data stored in the helper data storage and regenerate the original response. So for example, if you've got 2 errors and your correction code can correct 2 errors, and that's fine. If you've got 3 errors, but your correction code can only correct 2, then you can't generate the response. So it's important to really carefully choose the correction code. Now, the other application of PUF is for entity authentication. Nowadays, there are many situations where the identity of a physical object needs to be authenticated or checked. That includes things like e-passport, smart card, portable health monitoring system. In some cases, IoT devices used for security application. And in these cases, the classic approach is to use either symmetric or asymmetric cryptography. Now, the problem with this technique is that in some situation, if the devices that are meant to be identified are resource constrained, the classic crypto algorithm can have prohibitive implementation costs. Okay? So you can't simply afford to use them. And there are some other solutions based on light ciphers, and depending on which cipher to use, but they are not, they can't be all the time trusted. And the other problem with using this approach for authentication is that it relies on effectively storing the encryption key on the device itself. And we have already seen that this might not be secure. There are already attacks that can actually seek information from. Now, again, PUF can be used in this kind of situation. So what we need to do, the authentication authority required to actually communicate with the devices will embed a PUF in each device, and then they will need to characterize its behavior. In this case, we need to use a PUF that has many responses and many challenge and response. Sometimes these referred to as strong PUF because they have to be, maybe the device will have a long lifetime, so we need to communicate with it for a long period of time, and we should have enough challenge responses to do that. This is different from the use of PUF in cryptographic generation. In a sense, in that case, we don't need a PUF that has many challenge responses. We can use something like SRAM, which sometimes referred to as a weak PUF. Now, once the characterization is done, you deploy the device, and if you want to authenticate the device, then you send it a challenge effectively. You'll apply this challenge to its PUF. You receive the response. You compare the response with that stored in the database. If there is maybe 80% match, you say, well, that's fine. Now, the exact margin of error will depend on your system and what false admission rate and false rejection rate you want for your system. So if your margin of error is too large, if you allow maybe too many errors, then you might have risk falsely admitting kind of malicious devices. If your margin of error is too low, you're risking rejecting kind of authentic devices. So there is a trade-off there. Now, this is really the basic protocol. And again, this is just for illustrating the concept. We have developed some protocol here at the University of Southampton to demonstrate, to explore this idea that a PUF can actually be used to save, to reduce energy and computation resources. And this is one of them. It's called Ashura. It's based on combining PUF with a lightweight symmetric cipher, and it can perform mutual authentication. Now, we have done security analysis using cipher against a number of threats, which are typical for this type of applications. Eavesdropping, man in the middle, repair attack, model building. We talk about model building when we talk about security of path. And then we compared the energy, the power consumed for each authentication cycle between the proposed protocol and also some of the standards that such as PTLS. And we found that there is actually potentially significant benefit in terms of energy resources for using this type of path in this type of application. Again, there is also saving on memory resources. The third application for PUF technology I would like to discuss today is anti-counterfeit chip design. The problem here is that integrated circuit has become a multi-business, international distributed business because of this constant drive to reduce cost. So, so there is a high level of outsourcing when it comes to the IC supply chain. So before a chip end up in a product, it pretty much travel all around the globe. And because of this multinational nature of IC supply chain, then there are a number of security risks. And one of those risks are basically counterfeiting. And in particular type of counterfeiting is called basically overproduction. And overproduction, the threat model here is that you have a malicious factory that produces the quantity. So normally with IC design, you develop your design and you send your design file to the manufacturer, and they will produce chip based on files. But some of them might be tempted to produce extra chip, which will be sold in the black market. Why this is bad? This is bad because it causes, it potentially causes significant financial losses to the design house, and it can also cause reputational damage because some of these counterfeit overproduced IC, they do not actually follow the rigorous testing procedures an authentic IC will have to follow. Therefore, some of them might not actually work, and that ultimately affect the application, the design house. So in this context, PUF technology can be used to give the designer or the design house control over how many chips can actually be fabricated. I would say, to be more precise, how many chips can be functional after fabrication. And again, I will give you an example of how this can be achieved. So assuming you've got a design here, such as typical sequential state machine in this light gray area, what you do as a design house, you add some extra state. This all black states are all non-functional states. And then you embed a PUF into your design, which will initialize your flip-flop or the state machine into a non-functional state. Once the chip is fabricated, the chip will actually remain in non-functional state until the manufacturer will have to contact the design house, which provide basically a locking key to bring the chip from the initial non-functional state back to the functional state. And the assumption here is that only the design house will be able to do so because the manufacturer will not actually have control or knowledge, sufficient knowledge to do that. Another approach which we have developed it at the University of Southampton is to actually build a tracking system using blockchain technology and smart code execution refinement, which the tracking system will track the item through a supply chain and will identify each item based on its path. So each item, each product will have its own path. And you can think about this in a sense that you've got maybe construct a system on chip and you're sourcing different ICs from different suppliers, and you want to basically make sure that what you receive is what you is an authentically generated device. So this system will allow you to track these devices across the supply chain and reduce the possibility of tampering or basically or counterfeiting in IC supply chain. And it can also be applicable to other supply chains. The fourth application of PUFS that I would like to discuss, and this is also pretty much in use now by some companies, is anti-tamper. And in this case, there's a certain product that, especially high-end product that can be used in defense applications, they need this sort of protection. So they need to detect whether anybody is trying to physically tamper with them. So in this case, what we do, we use a coating puff. So this is simply some metal structure, which is based on the top metal layer of the chip. And if and then this metal structure will have particular capacitances, which is unique for each device, with of course variation. And if the adversaries try to actually tamper with the device or from reverse engineering, any form of physical attack, then this can be detected. And then the tamper response can be arranged accordingly. Now, as I mentioned, this sort of solution is already used, but there are also some in industry, but there are also some academic papers which implemented similar solution, kind of more full implementation of this solution, and this is one of them. It's called battery-less tamper-resistant global path. The idea is exactly very similar. In this case, we've got a full coat which include a mesh of metal lines, so it can and we observe, it can detect any tampering, measure the capacitances, and also there is a short or open connection. Right. Now, the third part of this talk is going to look at outstanding, challenging, and possible solutions. Now, the first challenge I'm going to discuss is the reliability. And PUF, as any integrated circuit, is vulnerable or subject to a number of reliability problems, environment variation, radiation, thermal noise, ground bounce, crosstalk, you name it, aging, and all of these can potentially lead to erroneous response. Now, if this is, the impact of this error is different from one application to the other, but in particular for cryptographic integration, we can't afford to have any errors. So, what is the state of art in terms of PUF reliability? This is this graphs here show the native bit error rate. So this is the error rate from different design, and this database is being prepared by Professor Massimo Aliotti from National University of Singapore, and it's basically, you can see that most of the design that we still have from fields such as RRM base, for example, we still have quite large bit error rate. Okay, so this is still pretty much a problem. Now, how to deal with it is another matter. You don't have to always worry about reliability, but if you do need to use PUF as a root key, then you have to assess it, and you can't always use error correction straight away because that might be very expensive. And this is the procedure you need to basically implement, or you can implement. So you can, after the chip is fabricated, you can apply some pre-processing steps. So before you deploy the chip, you basically implement, for example, aging acceleration. So if PUF is affected by aging, you can accelerate the aging process. And as some of you might be aware, that aging will actually, the impact of aging will saturate after a period of time. There will be an initial degradation, change in the threshold voltage of transistor as a result of aging, and then that will actually stop. So if we age the PUF, then at the beginning, then we don't have to worry about how aging is going to affect it later on. So this approach can be used, but it has to be used selectively, just applied to the PUF itself, because it can't be applied to the neighboring circuitry. It will ultimately affect aging, ultimately affect the performance of circuits. And then after that, you can apply stable bit selection algorithm. There are a number of these algorithms that can be implemented. So the idea here is to basically only choose the responses that are stable. So the PUF might generate, I don't know, 500 responses, and maybe 300 of them are stable and 200 are they constantly generate errors. So you can basically discard these two. And then after that, you have reliable response to reproduction using error correction code, other tolerance techniques such as redundancy-based, information-based redundancy correction code, or temporal-based redundancy, hardware-based redundancy. At the end stage here, the entropy of the response might actually be reduced. So we need some form of entropy compression or privacy amplification. It could be just simply a hash function. But again, something that you always need to keep in mind is the cost. Okay, we need to keep the cost down. So how much improvement or how much reduction in the bit error rate we can expect from each of these techniques? Now, there have been work by IBM a few years ago, 2016, and which looked exactly at this aspect, and it was focused on SRAM. So by applying BTI aging acceleration, they have managed to reduce the bit error rate by 1.4%. By combining aging acceleration with dark bit selection, the reduction was around 5%, and then at temporal majority voting, the reduction was around 7.5%. So you can, by using all these approaches, you can really reduce the bit error rate, therefore reducing the requirement for error correction code. So you don't need to correct as many errors. So therefore, you need to use smaller error correction block. In terms of security, and that's an important topic when it comes to PUF, because the whole idea of PUF is to provide more security, but we need also to make sure that the PUF itself is secure. So how do we judge whether a PUF is secure or not? We need the PUF for it to be secure. We need to know exactly what type of adversary we're looking at. Depending on the adversary, we can might have different type of attacks. We need to consider all the known attacks. So if we already know that PUF is vulnerable to a known attack that can't be secure, we can also use some quality matrix to assess that. So there are different types of adversary that can be considered. So eavesdropping adversary is somebody who's just listening to the communication between the circuit or the device containing the PUF and whoever is communicating with it. And we've got black box adversary, and that have access to the external input and output of the device. And then we have a white box adversary who has actually full access to the device and internal wiring, so they can actually probe the actual path inside. Now, what are the attacks that we know about? The major attack, one of the most major attacks, is mathematical cloning. Effectively, and that applies typically to strong path, or path that has many responsive challenges. Because if you are able to collect large number of responses and challenges, and then you feed that into a machine learning algorithm, you can basically build a mathematical model of the path that with high accuracy. And that's problematic. We have also some side channel attack. So side channel attack can actually use code injection, power analysis, and maybe combine that with mathematical cloning to improve its efficiency. We have helper data leakage. So it's important. I would say it's theoretically very difficult to actually prevent helper data leakage. So these are theoretical attacks, but you can do a lot in order to make this type of attack practically very difficult, which might be sufficient. And we also have physical cloning. So we have devices that can actually, that can be physically cloned, although they are unclonable, but they actually can be physically cloned. So the table here shows you just the attack type, and for each attack type, what kind of adversary that can wage this attack, and the sort of compromised security matrix in each case. So for mathematical cloning, this can be weighed by any attacker, so by snooping or black box or white box, and it affects all type of strong PUFS, and it effectively undermines both the unpredictability. We can build the model that can predict the responses and uniqueness of the path, because we created a clone of it. In terms of side channel attack, we need adversary to have physical access, either as a black box or as a white box, but it can also be used in combination with mathematical cloning to actually undermine both uniqueness and predictability. And we have the physical cloning attack, which we have already published a physical attack that managed to actually clone both the Arbiter and an SRAM path, which undermine all security matrix. This is effectively some example of attacks. So here we've got a 128-bit Arbiter, which is being cloned using evaluation strategy technique. So the mathematical model can have an accuracy of more than 90%. A link of the work, and we needed for that 150K. So challenge and responses. We have here physical characterization. So that's basically creating a physical, effectively a physical clone of the Arbiter, and that requires significantly less challenges and responses. We have physical emulation. So here we're emulating an SRAM path, and we can produce 100% accuracy. And using deep neural network, we can actually also create a mathematical model of some of the paths that are resilient to traditional type of machine learning algorithms. The model with actually 96.7. Now, it's worth saying that there isn't really now a path that's completely secure against a white box based mathematical cloning attack. So, in a sense, if the adversary is assumed to have access to the internal wiring of the path, then they will be able to clone it, because it's relatively simple circuit. With deep learning, quite very feasible. But this sort of problem should not really stop the path from being used because we don't always have to worry about this type of adversary. Now, this is some of the techniques that we have proposed. So this technique is based on permutation or using substitution to combine with the PUF in order to basically protect against black box adversary trying to wage a modeling attack. So in this case, the adversary is not supposed to actually be aware of the internal architecture of the design. There's also ongoing work looking at using multi-stage PUFs, so combining different PUFs, in this case RO, and this has generated some promising results, effectively reducing the predictability of the model to around 60%. We haven't tried it with US machine learning algorithm, deep learning, for example. Again, we are also looking at RAM PUF, and this is actually one of the PhD student working environment. So they're looking at trying to develop a new architecture for RAM PUF, which are stable, because this is one of the most promising architectures for reliable PUF. Open research questions. So there are still some outstanding challenges, and we are working most of them. So the first challenge is how to reproduce the PUF response reliably and at low cost. We know how to reproduce it reliably, but we don't necessarily know how to actually produce it reliably and at a low cost. How to prevent the helper data from revealing the PUF response. That's also a challenge that's worth considering. In this case, as I mentioned, it might not be theoretically possible to completely prevent this type of attack, but it can be made much more practically hard to wage. How to combat modeling attacks without incurring large unaffordable costs. Well, modeling attack can actually be prevented quite easily by increasing the complexity of the design or adding extra blocks. But that the whole point of using the PUF in the context of authentication is for resource-constrained application. So if the cost of using the PUF outweigh the cost of using maybe symmetric or asymmetric authentication-based scheme, then that's not good. So we need to find a cheap way of doing that. And finally, how to improve the efficiency of the PUF characterization stage, because that's something needs to be taken into consideration, especially if we're looking to deploy the PUF in a large number of devices. Do we need to, how many challenge responses do we need to collect? Can we do that efficiently? Finally, you need to know more. This is I've written a couple of years ago on this topic, which can discuss most of the topic that we have presented today. That's the end of the presentation, and I'm happy to take questions.
Basel, thank you for your presentation. So, are there any questions? If you have a question, just unmute yourself.
Right. So let me ask a question. So for authentication using PUF, right? My understanding is a user has a PUF, and then the service sends a challenge, and then the user uses this challenge to compute a response. And then how would the server check the response?
So the server, so what happens before you deploy the device, the server has to basically characterize the PUF within the device. So it will have to collect, this is what I refer to as characterization. So it has to characterize the behavior of the PUF, so collect large number of challenges and responses. and store them at the server, and then it will communicate with the device later on in order to basically ask it to generate a response and then compare the generated response with that stored on the server.
Right, right. Okay, okay. Now I understand. So, right. Okay. Another question is about this mathematical modeling attack. So previously I thought this path is a random one-way function essentially. So whatever the input is actually independent of the output. The output is independent of the input. But if you can use neural network to actually build a model, then that means the outputs and the inputs are dependent. So
ultimately, there is a dependency. That's the problem. So at the heart of it, PUF is simply an integrated circuit. There is a dependency, some dependency, input and output, and that can be captured by a machine learning algorithm. If you increase the complexity of the design, then you basically all you're doing that you're increasing the time needed to actually build the model. But the latest kind of deep learning approaches, there is no path that can actually withstand this type of attack. But the good news is that we don't always have to worry about it, because it might simply be infeasible practically. You can't wait for a long time to collect these challenge and responses. So there are ways around it, maybe at the protocol level. But if you are talking about white box adversary, that actually have access to the underlying path, then that's quite hard to actually protect against.
Okay, so yeah, that's okay. But if we compare that to cryptographic algorithms like AES, right?
Yeah.
This type of neural network attack won't be able to work. For example, if you give a lot of plaintext and ciphertext pairs to a neural network, the neural network won't be able to learn how to decrypt a ciphertext.
Because AES is much more complex, and it's based on an algorithm, an encryption algorithm.
Yes.
We're simply harnessing process variation and generating a response.
Then the question is, if we use this path, for example, to generate cryptographic keys or to do cryptographic functions, how reliable it would be, or how secure it would be in terms of cryptographic security? So
as I mentioned, the use of PUF for cryptographic key generation is already being deployed. It provides better protection against physical attack than, for example, storing the key in non-volatile memory. Because if you store the key in non-volatile memory, you can use maybe data remnants attacks or other type of physical attack to retrieve the data. The data is there. If you use the PUF, the response of the PUF is not always present. It's only generated when it's needed. And you can characterize the kind of, because you only need to generate one response. So it's quite feasible to actually using some error correction technique and other fault tolerance to generate a stable response based on this path.
Right. Yeah, I guess one question or one research direction might be how to properly model a path in a formal model, because currently my guess is that we just model it as a random one-way function, and then when we design protocol, we assume this path is one way and the output is random when the input is random. But this might not hold for the actual path implementation, and they might need some more thinking regarding how to model it properly. Otherwise, the protocol might be proved secure, but it's actually not, because the underlying assumption about path is not correct.
I think what you're intuitively, the matrix for the path is not whether there is a dependency between input and output. The matrix we use to assess the path is basically whether it's unique it's reliable, it's how the entropy of the generated response. So the response is supposed to be random but somehow reproducible, because it rely on the kind of, you apply the same challenge, you should be able to reproduce the same response.
Yeah, that's I understand. But when it's used in security applications, we actually sometimes need to assume they have some security properties.
Yes.
And those security properties probably need to be get more explicitly defined and match what exactly the path implementation actually can provide.
Yes, so that's why if you just go back, sorry, I'm just gonna go back to, because that's an important point you're making. So I'm just gonna go back to this architecture here. So this is, you add this stage here, this entropy, in order to make sure that the key, the resulting the key you're actually using for encryption should match the requirement by the encryption algorithm. So
okay, yeah.
So that's how this is tackled.
Right. Okay. Yeah. Thank you.
Yeah.